Hello method students. In this video we're going to be continuing to look at binomial probability distributions. In this section we focus on the graph, the expected value, the variance and the standard deviation of these things. Starting with the graph, now this is not something that you'll necessarily get many questions about, but it's good for your understanding to learn about it. If you actually set up like a histogram to give a visual description of the shape of a binomial probability distribution, I guess how that histogram looks is going to depend on what the probability of success is. And this is kind of a complicated looking section here, but if we look at three different examples, and the writing's not super clear, but in these examples we're looking at a binomial distribution where the number of trials is 10, right? Which obviously means that the number of successes we get could be anywhere from 0 to 10. The first histogram here shows a probability of success that's less than a half. So maybe a probability of success of like 0.2 or something like that. And what that shows is that if you, I guess, look at the probability of getting each of these outcomes, of getting 0 or 1 or 2 or 3 or 4 out of 10, well, the probabilities are more sort of skewed towards the bottom end, right? There's more chance that we'll get 1 or 2 or 3 successes if the probability of success is low, right? Again, this one, the writing's not super clear. This one was actually p equals 0.25. If the probability of success is equal to 0.5, then your binomial distribution here will actually, or distribution of the probabilities will be symmetrical, right? Because the most likely outcome is you'll get 5 successes out of 10. And then as you sort of go either side of that most likely outcome, the probabilities kind of decrease in a symmetric way on either side of 5. This graph here shows p equals 0.75. And you can see that now these probabilities are higher towards the upper end of the number of successes. So you're more likely to get sort of 7 or 8 successes out of 10 than you are to get 2 or 3 successes. Again, like I said, it's sort of a complicated way of representing this idea, but the idea I think is pretty intuitive, that basically the higher the probability of success for each trial, the more likely you are to get more successes. Okay, moving on to the mean, variance and standard deviation. With binomials, these are 3 relatively straightforward formulas that you just need to apply. When we talk about the mean, another way of saying that is the expected value. And so in a binomial distribution, that's the expected number of successes when you're running a trial multiple times. And the expected value, or the mean, is often represented with this symbol here, which is called mu. It's like it looks a bit like our letter U, but with this sort of extra tail at the front of it. So it's called mu. So if you see that, that just means the expected value, which can also be written as E of x. And the rule is that that's equal to n times p. So it's just equal to the number of trials times the probability of success. The variance is represented with this symbol sigma. Sigma squared represents the variance. That can also be written as VAR of x. And that is equal to NP times 1 minus p. So it's the number of trials times the probability of success times 1 minus the probability of success. And standard deviation is the square root of the variance. So you'll notice that the variance is written as sigma squared. The standard deviation is just written as sigma, or sometimes it's written as SD of x. And that's just equal to the square root of the variance formula. So once you know the variance, you can find the standard deviation by just taking the square root. Now, it's important to understand that the variance and the standard deviation are both measures of spread. They're measures of, or they give us an indication of how big a range of results we might expect. So if the variance and the standard deviation are high, it means that there's quite a big range of how many successes that we're likely to get. If the variance and standard deviation are small, it means we're expecting there's a bit more accuracy in terms of the range of successes that we might have. All right, as always, hopefully when we put these into practice a few times, you start to get the hang of it. So This first example, we've got a tennis player who hits 60% of his serves in, and the question is saying if he has 30 serves, how many would he expect to land in? So this is asking us about the expected value, or the mean. And so the mean, which we can also write as expected value of x, that's just equal to n times p, number of trials times the probability of success. So that's just 30 times 0.6, right? Because we had n equals 30, p equals 0.6. And so 30 times 0.6 is 18 serves. That's how many serves he would be expected to land in out of 30. Second example, at a particular workplace, the probability of an employee contracting influenza this winter is known to be 0.2. There are 100 employees in this workplace. Okay, so we've got P equals 0.2, N equals 100. And the first part of the question is saying how many employees are expected to get influenza this winter. So again, that's the expected value. So we can say expected value equals N times P, which in this question is 100 times 0.2, which is 20 employees. Okay, part B, find the variance and the standard deviation. Okay, so if you have to find both of them, it's always easier to find the variance first. All right, remember that the variance was represented by sigma squared, or we could also write it as VAR of x, and that is equal to NP times 1 minus P. All right, that was just the formula from the previous page. And so in this question, that's 100 times 0.2 times 1 minus 0.2, which is 20 times 0.8, which is 16. So the variance in this question is 16, the variance of the number of employees who would be expected to get influenza this winter out of this sample. The standard deviation, which we just write as sigma, is equal to the square root of the variance. So that's just the square root of 16, which is 4. So the standard deviation is 4 in this question. Alrighty, third example, we've got this time a basketballer, and the probability of this basketballer named Shaquille successfully making a free throw is 0.45. Right, so our probability of success each time this guy takes a shot, his probability of making it is 0.45. So we have P equals 0.45. In a particular game, he attempts 20 free throw shots. So N equals 20. If X represents the number of free throw shots made, find the variance of X and the standard deviation of X. Now this is pretty similar to what we just did in the previous example. So we start with the variance. That's equal to NP times 1 minus P, which is 20 times 0.45 times 1 minus 0.45. And this one says it's a calculator question, so we can use that to make sure of it. 20 times 0.45 times 0.55 equals, oops, should have shown on the screen there, 4.95. And then, of course, the standard deviation of X will just equal the square root of that answer. So the square root of 4.95, which is approximately equal to 2.225, let's say. Okay. Part B of the question says it is usually assumed with 95% confidence that the number of successful trials will be within 2 standard deviations of the mean. What is the 95% confidence interval for the number of free throws made by Shaquille? So what that means is if we start from the mean and go 2 standard deviations below and then 2 standard deviations above, what are those 2 numbers going to be where we can say, well, we're pretty confident that he'll make between this many and that many free throws? So what we can do first, because we haven't already got it in an earlier part of the question, is actually work out the mean or the expected value of X, right? Remember, that's just n times p. So in this question, that is 20 times 0.45, which is equal to 9. So we're expecting him to make 9 free throws. That's the expected value, or the mean. But to get this 95% confidence interval, what we do is we say, okay, well, the mean minus 2 lots of the standard deviation gives us kind of our lower limit, and then the mean plus 2 lots of the standard deviation gives us our upper limit. And so what we can say is, we could write it like this. We could say the mean minus 2 standard deviations. All right, so on our calculators, we can do the mean, which was 9, minus 2 times the standard deviation. That gives us 4.55. And then the mean plus 2 lots of the standard deviation. So same calculation, but with a plus, gives us 13.45. Okay, so we can write this a couple of ways, but what this is saying is that we're 95% confident that he's going to make, the number of free throws that he'll make will be between 4.55 and 13.45. I can write that like this. Probability that 4.55 is less than x, which is less than 13.45, is approximately equal to 0.95, or 95%. But obviously in practice, there's no way that he can make 4.55 free throws out of 20. So really this is saying it's the probability that x is between 5 and 13 inclusive, right? Because in order for him to make more than 4.55, well, he really has to make 5 or more, or to make less than 13.45, he has to make 13 or less, all right? So that's a way of writing that as a probability. The question said, what is the 95% confidence interval? Well, the interval is, and we can write it like this, we are 95% confident that he will make between 5 and 13 free throws. I'm going to write inclusive here. I'm going to say inclusive because we're including the 5 and the 13. So our 95% confidence interval is this interval here, right? X is between 5 and 13 inclusive. All right, lucky last example. This one, we don't really have much of a context. We've just given some values and we have to find the values of n and p. So we're kind of working backwards with this one. This one tells us that x is a binomial variable where the mean, the expected value, is 8 and the variance is 4.8. So what we can do here is say, okay, well, if we already know these values, we can just sort of substitute them into our formula. The mean is normally just n times p, and we're being told that that equals 8. And then the variance is normally equal to n times p times 1 minus p, and the question's telling us that equals 4.8. And by writing that out, we actually get two simultaneous equations with two unknowns, n and p, and we can just try to solve those equations. Now, one of the nice things about the two formulas is that the mean, the expected value, np, actually appears in the variance formula. So you get a nice kind of substitution that you can make where you can sub in np equals 8. So I can just substitute this first equation into this second one really easily and say that 8 times 1 minus p equals 4.8. And now I've just got an equation with p to solve. So I can divide both sides by 8 and get 1 minus p equals, now 48 divided by 8 would be 6. So 4.8 divided by 8 is 0.6. And then I can add the p over and subtract the 0.6 and we get p equals 0.4. can then sub that back into either equation, but it's going to be slightly easier to sub it into the first one. And we can say that n times p, so n times 0.4 equals 8. Therefore, n equals 8 divided by 0.4, same deal as before. 8 divided by 4 is 2, so 8 divided by 0.4 would be 20. Okay, so n and p, n is 20, p is 0.4. All right, so that's just an example. Like with a lot of formulas, often there'll be trickier questions where you actually have to use them to work backwards and find a missing value from those formulas. All right, so I hope that gives you a good sense of the mean, the standard deviation, and the variance. As always, if you need some help, please contact your teachers. But otherwise, good luck with exercise 14b.